Hello, students. The regulars are here. You guys make my day brighter. Just wanted to say that.
I have a quick question.
I might have an answer.
Are we doing lab on Friday?
So lab on Friday lab's in a weird place right now because our scheduled lab is a stoichiometry lab where we're doing something called limiting reactant stoichiometry. And we're not far enough along in what we've learned in class to be able to do that lab and handle the calculations yet. So here's what I'm thinking, and I wanted to get you guys' advice about this. I'm thinking Veterans Day is tomorrow anyway, so some of my sections don't get to have lab, and my labs are going to be out of sequence if I run labs some days and not on Thursday. The problem is we have an exam scheduled for next weekend, not this coming weekend, but the weekend after that. So it'll be pretty busy if we have lab, but we've got to have lab one of the 2 weekends or one of the 2 weeks. So I'm thinking about moving the lab to next week and just not having lab this week. And as a way to make sure that there's not too much to do at the end of next week, extending the time over which you can take the exam all the way through the end of Sunday instead of just Saturday. So giving people an extra day so they can take it anywhere Friday through Sunday, which means that they'll have an extra day to study if they want to make up for the fact that they've got to attend a lab for the week next week. How does that sound to everybody? Does that sound like an okay compromise? Because otherwise we're just like in a place where we would do the lab and not know how to do any of the calculations that surround it yet for like another week. Mia says, okay. Rudy is nodding yes. Katie and Jillian, what do you guys think? Yes for Katie, Jillian. At this point, we're like 3 out of 4. So yeah, okay, great, fantastic. So we're just not gonna have lab this week, all right? That's gonna keep things on a better schedule for all of my sections as a whole anyway. And we'll have the lab next week to do with limiting reactant stoichiometry. And since we're starting stoichiometry today, by the time we have 3 more meetings, we're going to be really good at stoichiometry. All right, like really good. So that's the plan. So we have now graduated out of chapter 5, which means that we know basically everything there is to know about bonding that, well, I don't want to say that. The physical chemists will attack me if I say it, but everything that we really have to remember forever about bonding, unless we're a physical chemist, we know at this point. All right, you'll learn more about molecular orbital theory if you keep on doing more years of chemistry major. But you've got all of the basics for how chemists regard bonding as happening like under your belt at this point, which is awesome. All right. Also, we've wrapped all the things that we're supposed to know for exam 2 at this point. It's just chapter 4 and chapter 5. That's it. It only sounds like 2 chapters, but as you know, chapter 4 is gargantuan, right? So it's a really good amount of material for an exam. Okay, so chapter 6 is where we start to talk about stoichiometry. Now, we've done this just a little bit already, all right? We've talked about the conversion back and forth between grams and moles of a chemical formula. We've used that mole concept to talk about groups of chemical formulas that have 6.022 times 10 to the 23rd individual units of that formula in them. All right. So we've learned how to do grams and moles conversions. Now we're going to apply them to more problems. Really, stoichiometry is just using the mole concept to keep track of how masses change when we go from reactants to products in chemical reactions. And also the mole concept can let us do some interesting things. We can apply it in ways that can help us to understand what a chemical formula might look like from some data. All right. So there are lots of things the mole concept can help us with. we're going to use it for lots of those things over the rest of the quarter. That's basically it. All right. That's the third exam is all about the mole concept and the ways that we can use it. So as a reminder, we have two different definitions for what a mole is. All right. 1 mole of any chemical formula is equal to the number of grams we get by adding all the average atomic masses in that formula. So it's good for us to review this because we haven't been thinking about it in quite a while. All right, so classic example, potassium nitrate. If we're talking about 1 mole of that formula, remember a mole can be abbreviated with M with a dash over the top of it. In order to figure out how many grams of KNO3 were in that 1 mole, we would have to add up all the average atomic masses in that formula from the periodic table. So potassium is 39.10, nitrogen 14.01, and then we have 3 oxygens that are each 16.00. So the conversion factor that we can use to convert back and forth between grams and moles of that chemical formula is that 1 mole of potassium nitrate is exactly the same size as 101.11 grams of potassium nitrate. We often refer to this as the molar mass of that chemical formula. All right, so molar mass is often written in units of grams per mole, the number of grams per every 1 mole of that formula. Mia, what's the smile for?
Because this is what I was asking earlier from the lab that we did last week.
What did we do last week that we were using stoichiometry for? I can't remember anymore.
Aren't we using it to get the formula mass or the product mass? For our magnesium oxide?
So yes, that's exactly right. Yep. So I showed an example like that of, what we call limiting reactant stoichiometry. But we know that in every one of the cases from last week, the magnesium is the thing that's going to run out, because either magnesium runs out or the O2, the oxygen in the air, runs out. And since none of us died when we were doing the lab, I'm assuming that the O2 wasn't used up in the room, right? There was still O2 left over. So because of that, yes, we're assuming that this is a limiting reactant problem, and magnesium in that problem would be the limiting reactant, okay? Yeah, we did do some limiting reactant stoichiometry, which is great. Everybody in the in-person lab section should be ahead because we've done some examples of that already, but we're gonna use this concept to do a lot more of that, Mia, all right? Like a ton more. Okay, so there is a huge list of things that that concept allows us to be able to do. I always like to skim to make sure that I don't miss anything when I'm looking for what we're supposed to be doing next. So when I looked over it, formula mass is what we just covered, the number of grams there are in every 1 mole of a chemical formula. So we've already knocked out one of the parts of chapter 6. Chapter 6 is pretty short, all right? Now, determining imperial and molecular formulas is just a little bit more difficult. It's another way that we can use this concept of converting grams into moles to tell us something about what the chemical formula of a substance might look like if we do analysis on it. All right. So one of the things that we do commonly in the world of chemistry is an analysis called percent composition. So there are instruments that we can use to analyze what percentage of each element there is in a chemical formula. All right. And if we know how to apply the mole concept, we can take that percent composition data, like experimental data about what percentage of each element we have in that sample, and we can turn it into something that we call an empirical formula. So an empirical formula is the simplest whole number ratio of atoms there are in the chemical formula. All right. Now, that's not always the same as the molecular formula, the full chemical formula. So here's an example. If we had the chemical formula N2O4, that formula in real life has 2 nitrogens, 4 oxygens in it. But if we were calculating the empirical formula or looking for the empirical formula, it would appear like this instead, because there's a 1-to-2 ratio of nitrogens to oxygens in the formula. So even though this has the same ratio, it's not the simplest whole number ratio. All of the atoms in that formula could be divided by 2. All right. So benzene, the molecular formula for benzene is C6H6. There are 6 carbons and 6 hydrogens in benzene. But the empirical formula for benzene would just be CH, because the ratio of carbons to hydrogens is a 1-to-1 ratio. It's the simplest whole number ratio of atoms is the empirical formula. So let's try to use the mole concept to take some data about percent composition for a formula. We don't know what the formula is, only what the percentage of each element is, all right? And try and turn that into the empirical formula of that chemical formula, all right? So these are hard questions to make up. So because of that, we're going to use Chem 101 and do a couple of problems that they've already got in the bank for us. There are also other ways to create your own problems, or you could use Khan Academy, has a ton of these also, all right? So there are lots of places to find problems like this. So we're going to create a new in-class activity. If I can type. And this should also show up for all of you guys unless I did the wrong thing and have the wrong class set. No, okay, we're good. So let's do one that's tangentially related first, all right? If we talk about the percent by mass of oxygen in this formula C3H8O2. Now, if we think about where the mass comes from, it's all of those atoms put together, all right? And we know that some atoms are bigger than others. How do we know how big they are? Based on their average atomic masses, right? So if we wanted to know what percentage oxygen was in this C3H8O2, we'd have to figure out how many grams per mole the entire formula was. And then out of that, how many of those grams are oxygen grams. All right. So in C3H8O2, if I'm calculating, whoops. Too much. if I'm calculating the molar mass of this compound, the formula mass of this compound, there are 3 carbons that each have an average atomic mass of 12.01. There are 8 hydrogens that each have a formula mass of, or an atomic mass of 1.01 for average atomic mass. And then for oxygen, there are 2 oxygens that each have an average atomic mass of 16.00. So if I put all of those masses together, that's going to tell us how many atomic mass units one of these things would weigh, or it could also tell us how many grams there are in 1 mole of that formula. It's the same number. I'm doing that in my head. Hopefully you guys are getting the same thing as me. Okay, awesome. So if this entire formula has a formula mass of 76.11 atomic mass units, or a molar mass of 76.11 grams per mole, what fraction of that is oxygen? Just this part right here, right? Those 2 oxygen atoms that each have an average atomic mass of 16 grams per mole. So those 32.00 grams are the 2 oxygens. And that's the fraction out of this total mass that is oxygen. We always turn a fraction into a percentage by multiplying by 100%. So my calculation is saying that 42.0% out of that formula's mass is oxygen. All right. This number might be a number that we would get out of a chemical analysis of this compound. It would say that it was 42% oxygen. And we could also calculate what percentage each of the other parts was as well. So let's do that really quick, because that's the data that's going to go into our calculation the next time we do this. All right. So let's figure out what percentage each element is here. All right. So our carbons are 36.03 grams out of the 76.11 gram total. We turn that fraction into a percentage by multiplying by 100%. Running out of space. Sorry, it's so small. I just can't. There's an end to the desk up there, so I can't push the paper any farther up. And then finally, for hydrogen, 8.08 grams out of the 76.11 grams are hydrogen. We turn that fraction into a percentage by multiplying by 100%. All right. So 42% by mass of this formula is oxygen. I'm getting 47.3% of my mass is carbon. And 10.6% of my mass is hydrogen. Now, roughly at least, these add up to 100%. All right, so just through rounding error, we don't have 0.1% of the mass accounted for. But if we kept more significant figures, then that would work itself out just fine. All right. So if we did an analysis of this, it's called elemental analysis, all right, to figure out what percentage of each element we have, we would get this data that said 47.3% carbon, 10.6% hydrogen, 42% oxygen. What do we do with that to get to a formula? All right, because that's more useful. That's how chemists use elemental analysis, is to figure out what the formula is of the stuff that they're working with. So let's try an example like that, where instead, and I have to stop the share for just a second, or else it might ruin the problem for us. Perfect. All right, I love this. What's the empirical formula of a compound that contains only iron and oxygen and is 22.27% oxygen? It doesn't seem like a lot of information, but since there are only two elements there, can't we tell what percentage of our compound is iron as well? Yeah, we just have to do a little bit of work. Okay, so there are lots of ways to solve this problem. Here is a way that I find pretty useful. All right, it's not the only way, it's just a way. It's a pretty good way. Using percentages and converting into numbers of moles, because we know from chemical formulas that we've looked at before, if we have, for example, 1 mole of methane, CH4, inside that 1 mole of methane, there are 4 moles of hydrogen, because there are 4 times as many hydrogens as there are methanes. All right. So in order for us to get information about this chemical formula, the empirical formula, we are going to have to figure out what the mole to mole ratio of irons and oxygens is. All right. The easiest way to do that is to start with grams and convert to a number of moles of iron and of oxygen. But I don't see any masses here in grams. I just see percentages. So we got to use our imaginations a little bit. All right. In our imaginations, we could say that we had a sample of this iron oxide, whatever its formula is, that is exactly 100.00 grams of that formula. So if we had 100.00 grams of that compound, how many of those grams would be iron? Wouldn't it be 77.73 grams of iron in every 100 grams of that compound? And it would be 22.27 grams of oxygen in every 100 grams of that compound. All right. So when we have percent by mass, we can just assume that we're using a sample that is 100 grams of the sample. All right. Doesn't really matter what sample size we use. So 100 grams is convenient because then our percentages just turn into grams of each of the things instead. So if we want to know what the mole to mole ratio of irons to oxygens is, the first thing that we're going to have to do is take these masses in grams and convert them into numbers of moles of iron and of oxygen. So every 1 mole of iron Our periodic table tells us that every 1 mole of iron has a mass of 55.85 grams of iron. We can use that as our conversion factor to convert those grams of iron into moles of iron. We could do the same thing with our oxygen. 22.27 grams of oxygen. Well, we know that every 1 mole of oxygen has a mass of 16.00 grams. That's right from oxygen's average atomic mass on the periodic table. So now we have solved for the number of moles of iron and the number of moles of oxygen in a sample of this compound, or at least we'll be able to after we put this into our calculator. So I'm solving and seeing that I have 1.39 moles of iron in this sample. And it looks like, holy smokes, I also have 1.39 moles of oxygen in this compound. So what does that tell us about the empirical formula? What we're trying to solve for is the ratio of one atom to the other. And it's pretty easy to figure out what the ratio is with these numbers, but let's actually set up the math just to be sure anyway. All right, so there are 1.39 moles of iron per every 1.39 moles of oxygen in this formula. So if I plug that into my calculator, there's 1 mole of iron per every 1 mole of oxygen in this formula. All right, a whole number ratio. Remember that every chemical formula has atoms put together in whole number ratios. All right. So if the ratio is 1:1, that means that there is 1 iron per every 1 oxygen in that formula, which means that FeO, the formula with 1 iron, I wish I could spell today. The formula with exactly 1 iron and exactly 1 oxygen is the correct empirical formula, the formula with the correct ratio, whole number ratio of atoms in the formula. All right, let's try another one of these. First of all, it's always good to get the kudos, the congratulations. We've done good work. Oops, I just added that. So let's show our answer. Sweet. All right, so I'm adding that to the list so that other people can tag along and try these problems later, just practice ones, all right? All right, let's give this one a shot. A compound that contains only carbon, hydrogen, and oxygen is 58.8% carbon and 9.87% hydrogen by mass. What's the empirical formula of this substance? Let's give it a shot. So I've skipped a couple of small steps here. How did I figure out what percentage of oxygen did I have? Well, I know that there's only carbon and hydrogen and oxygen, and we know the percentages of carbon and hydrogen. So whatever's left over has to be oxygen, right? The other step that I skipped is if all these percentages add to 100%, if I had 100 grams of that substance, that mystery substance, then this would be the number of grams of each element there would be in that 100 grams of the substance. All right, are we good with those two steps? Everybody okay so far? Okay, so let's try and finish this one up. I'll give you enough time to try and predict the correct empirical formula. So we're going to convert our grams of carbon to moles of carbon, because we know that the average atomic mass of carbon is 12.01. So there are 12.01 grams of carbon in every 1 mole of carbon. We'll do the same thing with hydrogen. Do the same thing with oxygen. Okay. So if we're trying to figure out the whole number ratio of atoms in this formula, the easiest thing for us to do is going to be to use whichever one of these has the fewest number of moles as the denominator to get our ratio. So there are 4.90 moles of carbon per every 1.96 moles of oxygen in this formula. So what does this ratio look like? 4.90 divided by 1.96. it looks like we've got 2.5 moles of carbon per every mole of oxygen in this formula. Now, this can't be the empirical formula because there's no such thing as half a carbon. So a whole number ratio would be a 5-to-2 ratio. 5 moles of carbon per every 2 moles of oxygen in that formula. All right, now let's try and figure out what our ratio of hydrogens to oxygens is. 9.77 moles of hydrogen per every 1.96 moles of oxygen. So it's not perfect. When I put this into my calculator, I get 4.98. We know that it has to be a whole number ratio. So what is 4.98 really, really close to in terms of an integer number? It's 5, right? About 5 moles of hydrogen per every 1 mole of oxygen. But we know that there's a 5-to-2 ratio of carbons to oxygens. So because of that, there have to be at minimum 2 moles of oxygen in this formula. All right, or else we are not going to have a whole number of carbons in the formula. So if our ratio is 5 hydrogens per every oxygen in the formula, and there are at least 2 oxygens in the formula, then it would be a 10-to-2 ratio between hydrogen and oxygen. So these numbers now allow us to complete the empirical formula for this compound, because in that compound we would have to have 5 carbons per every 10 hydrogens and 2 oxygens. So turning percent composition data into numbers of atoms in the empirical formula, that's one of the many ways that the mole can benefit us. All right, just by knowing what fraction of mass each of the elements is in this unknown compound, we can use the mole concept to turn that into an empirical formula. It's pretty impressive. All right, let's make sure that we did this correctly. Notice that there's a nice Fuller answer right here. So that is the correct ratio. 2.5 carbons to 5 hydrogens to 1 oxygen. But we know that in chemical formulas, we have to have whole number ratios, right? There's no such thing as a half a carbon atom. So 5 to 10 to 2 looks better. Awesome. We did good. All right, let's try one more of these together. And I'm going to try and give us one. Ooh, I love this. So this is also a nice little practice with our nomenclature. One of the things that we talked about very briefly was hydrates of ionic compounds. So what is a hydrate? It's an ionic compound that has some number of waters attached to it. All right. So this is actually an analysis that we do in the lab every year at some point. For those of you who are doing 162, we will do at least one analysis of the number of waters of hydration in an ionic compound that's a hydrate. So copper 2 sulfate is a classic example of this. And what we're able to figure out is that when we heat enough to drive off all of the water in that copper 2 sulfate sample, it looks like it's 36.08% water by mass. All right. So very similar concept, but we're going to apply our stoichiometry just a little bit differently here. So if we have a hydrate of copper 2 sulfate, it's going to have this formula, all right? Copper 2 sulfate and some number of waters along with. What I'm asking you to figure out is what's X? How many waters are there in this formula? Based on what fraction of this mass is water. So we know that 36.08% of our mass is water, which means that by difference, (63.92% of our sample is copper 2 sulfate. So very, very similar problem here. We need to figure out the mole ratio that there is here, right? How many moles of water are there per mole of copper 2 sulfate? Let's take a second and see if you can do it. So we can use the same trick that we used before, where instead of thinking about percentages, we'll just assume we have 100 grams of this copper 2 sulfate compound with some waters in it. And out of that, 36.08 of those grams would be water and 63.92 of those grams would be copper 2 sulfate. We can convert grams of water into moles of water by adding up all the average atomic masses in H2O to get the number of grams per mole, right? So 2 hydrogens that are 1.01 apiece, and then an oxygen that's 16.00 gives us that there are 18.02 grams of water in every 1 mole. And then for copper 2 sulfate, we'd have to do the same exact thing. It's just a slightly bigger formula, so it's a slightly bigger pain in the butt. If I'm adding up all the average atomic masses, we're adding up the average atomic mass of 1 copper, which is 63.55, and a sulfur, which is 32.07. I never remember that one, even though sulfur is my favorite element. I should memorize it. and then 4 oxygens that are each 16.00. So it looks like every 1 mole of copper 2 sulfate has a mass of 159.62 grams. So now we can solve for the number of moles of water and the number of moles of copper 2 sulfate there are in this compound. So I'm getting like about 2 moles of water. And about 0.400 moles of copper 2 sulfate. Remember, if we want a whole number ratio, we have to make our denominator whichever one of these has the least number of moles. So there are 2.00 moles of water per every 0.400 moles of copper 2 sulfate. As a whole number ratio, that's looking like 5 to 1, isn't it? There are 5 moles of water per every 1 mole of copper 2 sulfate in this formula. And that means we now know what the correct formula for our hydrate is. In this hydrate, there are 5 waters for every one of our copper 2 sulfates. So can you guys tell me what we would name this compound now that you have the formula? Little review from early chapter 4. It's never too early to start preparing for exam 2. So we would use the prefix to tell how many waters there were along with our ionic compound. We call this copper 2 sulfate because copper can have different charges. So we have to specify that the copper in this compound is a +2. All right, and then after that, the 5 waters. So we use the prefix penta after hydrate to talk about how many of those waters we have in our formula. All right, let's try one more percent by mass composition before Rudy has to get out of here. Okay, so I have a compound. let's make this bigger. Boop. All right. Unknown compound has 39.9% carbon, 6.70% hydrogen, and 53.4% oxygen. We also know the compound's molar mass is 60.06 grams per mole. There are instruments that give us both of these pieces of information very quickly about a compound. So the percentages are from elemental analysis. The molar mass is from a tool called a mass spectrometer. Mass spectrometers can be incredibly expensive. On the low end, we're talking $60,000, $70,000. That's very, very basic, not super useful, all the way up to millions of dollars for a very sensitive mass spectrometer capable of getting masses and chemical formulas for intact whole proteins.
I think I have it, but I'm almost positive none of my work is correct because I did it in my head.
Okay. So how did you do it in your head if you had to convert to moles and then get mole ratios of everything? That's crazy.
So 60.06, if you've got carbon and oxygen, you can only have 2 carbons, and then you have to have 4 hydrogens to make it the 0.06. And then I added the hydrogens and the carbons together to get that answer and subtracted it from 60.06 to get the oxygens. Acetic acid?
Well, that's the name of the compound, so it is the correct
Okay.
name. But I still don't understand how you did that in your head. That's really impressive. But the correct formula, we're going to have to get by a mole-to-mole ratio, right?
But like all of a sudden it just like moles completely went out the window. You gave me grams and my brain was just like, you have grams on periodic table. Do that.
So here's where things get a little bit silly, Katie, all right? When we use mole ratios to solve for a formula, we don't get the whole formula. We get the simplest whole number ratio. And here's a case where they're not the same thing, all right? The empirical formula is not the same as the molecular formula here. So that's the whole purpose for which I gave you guys this problem, and you circumvented it by not using the mole concept, so whatevs, all right? I'm not mad, I'm just disappointed.
To be completely honest, I didn't know my brain could do that, so I'm clueless.
It also probably has to do with just being lucky about these masses having some basic proximity to a whole number ratio as they are, all right? So
Nah, don't let him rob you. You're a savant.
Now, I'm not saying that her work in her head isn't impressive. It is. I'm just saying that the ability to do that with no matter what masses or percentages you're starting with, like I don't say it's impossible, but I know I couldn't do it. All right. So this is a way that no matter what percentages we have, we can still get usable data out of them. So I'm getting 3.33 moles of carbon. .63 moles of hydrogen. And 3.33 moles of oxygen. Sweet. So it's pretty easy for us to figure out what the whole number ratio is here. We could use carbon or oxygen as our denominator and it'll work out fine. So it looks like we've got 2 moles of hydrogen for every 1 mole of oxygen, and also 1 mole of carbon per every 1 mole of oxygen, because same number of moles of each. So that should be enough for us to get the empirical formula, CH2O. However, we also have the molar mass of the compound. So if I take the molar mass of this formula right here, we could just refer to that as the empirical mass, right? The molar mass of the formula that we see here. I have a carbon for 12.01 and 2 hydrogens for 2.02 and an oxygen for 16.00. So my empirical mass looks like 30.03. Let's compare that to the known molar mass of the compound. It looks like the known molar mass of the compound is twice as big, right? So since the molar mass of the compound is 2 times bigger than the empirical mass, that must mean that to get the molar or the molecular formula, we're going to have to multiply all of those atoms in the empirical mass by 2 to get the correct number of atoms. So our correct formula would be C2H4O2, which is the formula for acetic acid. We just don't normally write it that way. We separate out one of the hydrogens because it has special powers. So hopefully you guys are comfortable now with the use of the mole concept to convert percent by mass data into empirical or molecular formulas. All right, it's one of the many uses of the mole concept. Again, if I'm looking for all the uses that we're supposed to keep track of, and I actually like that the book has this little like sort of a reminder chapter of ways that we can use the mole concept before we get into full-blown limiting reactant stoichiometry. The next one of those ways that we can use the mole concept is with something called concentrations. All right, so concentrations are amounts of stuff per an amount of a solution.
Good night.
Good night, Rudy. That's bad. So if we're talking about the concentration of a solution, this is a mathematical representation of how much stuff is dissolved per an amount of the solution, all right? So we could think of that as an amount of the solute, the stuff that's dissolved in the solution, per volume of the solution. Let's think of a very simple example of us making a solution, all right? Let's say that we dissolve 7.55 grams of table salt. We're going to dissolve it into water to make a solution that has a total volume of 373 milliliters. So what's the concentration of this solution in grams of sodium chloride per milliliter of solution? Well, we couldn't have much simpler problem than that. We know how many grams of sodium chloride we put in. We divide that by the volume of the solution. So our concentration of sodium chloride in the solution ends up being 0.0202 grams of sodium chloride per every 1 milliliter of solution. So if I just took 1 milliliter out of that 373 and evaporated it, it looks like there would be 0.0202 grams of sodium chloride in that 1 milliliter of that solution. Now, the cool thing is that the units of amount of the solute and the units for the volume of the solution, those can be variable, and it's not really hard to convert from one unit to another as long as you remember how to do conversions from all the way back in chapter 1. So the amount of solute could be represented by grams or milligrams or kilograms or micrograms or nanograms or femtograms. We don't even know what the prefix femto means in this class yet. It turns out that there are 10 to the 15th femtograms in every 1 gram, all right? So a femtogram is really, really small. Like femtograms probably are on the order of like a good mass for single atoms, right? Another amount of solute measure that we could potentially use doesn't have to do with grams at all. So the amount measurement that we often use when we're talking about formula masses from the periodic table is a number of moles. A number of moles can be an amount of a solute as well. So often moles will be our amount of solute in the numerator of our concentration. Now, likewise, in the denominator, volumes are normally in the metric system going to be either liters or some prefix with liters, like milliliters, microliters, kiloliters, all right? So either liters or some prefix with liters. Now, the cool thing is, it's very easy for us to convert from one concentration unit to another because we already know how to convert from liters into milliliters or liters into microliters, right? We can convert from any volume unit in the denominator to any other volume unit that we want to very easily. Likewise, we could convert from one of these units. I'm going to cross out femtograms because I don't really care if you use that one. All right. But these other ones, we could convert from one of these units to any of the others as well, because we know how to convert from grams into any of these other units. We also know how to convert from grams to moles, right? For any chemical formula. So let's do that and change this concentration unit just a little bit. So right now, my concentration of this solution is 0.0202 grams of sodium chloride per every milliliter of solution. I want you to turn this concentration into units of moles per liter. Moles of sodium chloride per liter of solution. So that's as simple as converting those grams in the numerator into moles and converting those milliliters in the denominator into liters. So take a second, see if you can do it. So in order to make this conversion happen, we're going to need two conversion factors. One to convert those grams in the numerator into moles. The other to convert those milliliters in the denominator into liters. All right, let's do grams in the numerator first. How do we convert between grams and moles? We have to know what the average atomic mass of all of the atoms in that formula. So we add together 22.99 for sodium and another 35.45 for chlorine. So every 1 mole of NaCl has a mass of 58.44 grams of NaCl. So it looks like our grams cancel and we're left with moles of sodium chloride in the numerator. That's great. Now we're going to convert our milliliters in the denominator into liters. So that conversion factor should look like this to get our units to cancel out. And we know that there are 1,000 milliliters in every 1 liter. So I'm calculating that we have a concentration now of sodium chloride of 0.346 moles of sodium chloride per every liter of solution. Now this unit, moles over liters, is a super useful unit for chemists to use, all right? Later on, after we've done some practice with limiting reactant stoichiometry, we'll also learn to use limiting reactant stoichiometry with concentrations. And the concentration unit of moles over liters is a really simple one to use to do stoichiometry with. So this is so common that chemists have abbreviated that unit as capital M. So if you just see like 0.346 capital M sodium chloride, that's another way of saying that there are 0.346 moles of sodium chloride per every liter of solution. All right. So that is actually a shorthand for a unit that has units in both the numerator and the denominator. Capital M is gram or moles over liters. That unit has the name molarity. All right. So the molarity of a solution is the number of moles of that solute per every liter of solution. Now, the cool thing is, like, we just started talking about solutions already, but they're really easy to deal with mathematically because we know how to do unit conversions from all the way back in chapter 1. We've been handling conversions like this forever at this point. Like from week 1 of the class, we've done enough conversions that we should be able to handle this. The only newer thing that we didn't learn in week 1 is how to do this conversion between grams and moles, right? So that conversion factor is one that we've now known about for a month at least, maybe more than that. So there's nothing new here. It's just being able to set up these conversions to get our units to cancel. All right. There's nothing new about working with solutions. We can change the units of amount of stuff in the numerator or the volume unit in the denominator any way we want to suit us for a problem that we're doing. All right. So let's do one more conversion where we're going to change from one unit into another. Concentrated ammonia, which is the chemical formula NH3, has a concentration of 12 moles per liter. What is that concentration in units of grams per milliliter? So it looks like we've got to convert those moles in the numerator into grams and those liters in the denominator into milliliters, and we should be done. So every 1 mole of NH3, we get the number of grams by adding the average atomic masses in that formula. So 14.01 plus 3.03 for the 3 hydrogens. So it looks like there's 17.04 grams of NH3 in every 1 mole. And then it looks like in every 1 liter, there are 1,000 milliliters. So I'm calculating a concentration of 0.204 grams per milliliter. Katie, cute dog.
Thanks. She's at the point where it's like, can you pay attention to me now?
Yeah. Hey, I'm cleaning myself. Watch. You guys don't see because it's under the counter, but like it's right around when class starts, when my cats always get hungry for their second meal of the day. So like halfway through class, they're coming in and like bopping me in the legs over and over again. So I'm trying to do math in my head while my cats are bopping me.
Fake love, like just coming around because they need something, trying to be cute.
They're
They know what they're
actually
doing.
really cute. Like my cat Mortimer, the gray one. I don't know if you guys have seen him yet. Mortimer, like anytime, not just when he's hungry. If I'm near him in the room, I can lean over and say, "Give me a kiss." And if I make a kissy noise, he will like lean up and like stand up on 2 feet to give me a kiss. It's pretty awesome. Yeah. So we're total buds.
Yeah, I rescued this one at 3 months, so she's attached at the hip to me, and I have to feed them before class so they don't come in here and ruin me because
Yeah.
my husky will ruin the background.
So we got Mortimer from the Humane Society in Skagit County, and we got there and he was in like a big room with like 12 other cats, and there was this one like big alpha female that was just like beating everybody else up in the enclosure. So Mortimer was like up as far away from her as he could possibly get, and the people said like this girl has been beating everybody else up, so that's why he looks kind of timid, right? So she had to like pull him out of his little hidey hole and sort of set him down in the room next to us, and he just like sat down like this, like, who's gonna come at me next, right? So then I just like picked him up for a second, and immediately he just like turned his head and like put it right into my chest. He's like, "Get me out of here, please." All right, just write it up, we're taking him. Yep. So like right away when I picked him up, he picked me.
That's exactly how I picked my cat like 12 years ago. She was climbing up the like they had him in like a big ferret cage because they were all 6-week plus, and she was climbing up the side, and I was like, "Mom, I want that one, the one that's trying to escape." I want to take her home. And so I picked her up, and she like attached to my sweatshirt and climbed up my shoulder and sat on my shoulder the rest of the day. I was like, "Okay, yep, she's mine." That's what I want.
So 2 cats ago was a cat that I had like for all of grad school, and then like probably the first 7 years that I was a professor. And when I went to the pound, it was there, the pound to adopt that cat, the person that was like in charge was picking up all the cats to like show them to me. And most of these cats, when they were just like going limp and not like showing any sign of life whatsoever. It's like they'd given up. Well, she picked up Timid, and Timid immediately like turned around and went, "Wow," and like tried to go at that. I was like, that's the one I want right there. Like this cat has spirit, right? And she did. She totally had spirit. So now we're on an all male kick because it's easier to get males to bond with one another than it is to get to introduce girls and guys to one another. So Timid got along really well with Oscar, but when Timid passed away, we wanted to get another cat that was a male because I don't think Oscar would have liked another girl in the house. So that's when we got Edgar, and then Oscar passed away, so we got Mortimer. So now it's Edgar and Mortimer. We just keep a cycle of strays running through the house 2 at a time all the time.
That's what I've done my whole life. We've had at least 2 dogs, and then when I got to high school, we had my cat from when I was a baby, and then I got my cat, and now my mom has my cat, and her dog, and I have 2 dogs here. If I could have my cat, I'd have her with me, but base housing, and I don't want to get in trouble.
Yeah. I didn't know they didn't let pets in base housing. That sucks.
You can only have 2.
Oh,
It
okay.
doesn't.
Well, that's decent. I mean, they just
Yeah.
don't want crazy cat lady happening.
Yeah.
So out of my family, I would be the crazy cat lady. My wife is the one that has the hard 2 cat limit.
Really?
Oh yeah, I would be the crazy cat lady for sure. I'd have a dozen if I could. I love cats.
Oh, I would totally have 3 or 4 dogs, but my husband's we don't have the yard for that, and housing walks by all the time, so no.
Mia, do you have any pets?
Yeah, I have 2 cats. I have
Sweet.
2 cats. Here's one. Come here, cat. Oh God. Oh God, no. Cat, don't embarrass me. This is Cat.
Your cat's name is Cat?
Yeah.
That's awesome.
And I have another one named Grady. And this is my cat, Allie, who passed away.
Aww.
You know what? I love that idea. I don't have any tattoos, and I've been thinking for a long time about what would make sense for one, because I'm not opposed to them. I think they're really cool. Body art is awesome, but I never thought of anything that meant enough to me that I would want to put it on myself. But portraits of my old cats, that is kind of a cool idea. So maybe I could do an arm sleeve where I could start out with one and then have the successors going all the way down the arm, because I've got enough of them at this point. I could do a whole arm sleeve with cats that I've had.
That's awesome.
That would be so sweet.
It would be really awesome. I'll have to talk to my wife about that. And then there's other considerations do we do color or just black and white? What art style, right? Do we want hyper realist, or do we want caricatures of the cats?
Maybe based on their personalities.
Yeah, I don't know. So I've got stuff to think about. Mia, you've made me start thinking now. So if I end up, I'll show you the tattoo if something comes of this.
I have a big portrait, but it's of a horse that I used to train, and it's on my side, so no one sees it. But yeah, it's ginormous.
Sweet. And what if somebody sees the cats on my arm and they're if they don't like it, then they're not my person anyway, because if people don't like cats, then I don't want to talk to them.
Yeah, is that a real thing? Are people really into
people that are super into dogs a lot of times don't like cats because they don't like animals that actually have some level of independence.
Yeah, that I guess I could see. I don't know, but that's still really bizarre.
Who needs that kind of negativity in their lives?
Yeah.
All right, y'all. That's probably enough example problems for today. We covered a lot of chapter 6 already. So we'll probably finish up chapter 6 next Monday and then do some more. What's today? Today's Wednesday. Yeah. So we'll finish up chapter 6 next Monday and also probably get well into chapter 7 at the same time. Okay. So that's our schedule. And remember, no lab this week, lab next week.
Yep.
Okay, but the lab that we did last week, is that still due?
It's going to be due next Friday.
Next Friday, okay.
Yeah, because then
Are you gonna open it to be due next Friday? Because I'm got all the calculations done and everything like that, so I just wanted to.
It'll be due next Friday. So the due dates in Canvas are, I don't want to say it's just a recommendation, but even if it marks it late, it doesn't change anything about the way the assignment is graded.
See, I
Okay.
don't even have the option to like turn it in or like there's a submission button. Like I don't have it on mine.
Really? You should.
Yeah.
It should accept late assignments for forever, so
I
maybe
can't
it's
even, like,
something wrong with, okay, well, I'll check on that,
Yeah.
okay? Is it for,
Okay.
what assignment are you talking about for, Katie?
lab 7. The one that we just did, because I just wanted to turn it in, but it doesn't even have the ability to turn it in. Hold on, I'm talking to
Yeah,
my-
for me too.
Whoa. Okay, weird. Yeah, thank you for letting me know about that. I didn't know about that till just now, so I'll check and make sure that it's functioning correctly, because it obviously isn't right now.
Okay.
Okay,
Perfect.
all right, thank you, guys.
Thank you.
Bye.
Bye.